Okay, thanks Alex for the introduction. So I want to thank the organizers of this colloquium. It's very nice to be here and talk to real people after a while. So I'm very pleased to present some recent experiments that we've been doing in collaboration with the MPQ, my lab at Université de Paris, and Lipsys in Jussieu, and as well as Nokia in Saclay. So this talk will be mainly about quantum communication, and I'm going to show you how we can build a quantum network based on miniature photonic chips. So we've been hearing about quantum networks and photonic chips in the last two talks, so I hope you will find this interesting as well. So if you're here, you should have heard about, of course, quantum technology, so very prominent field in physics, which is often divided into four main research directions, so computing and simulation, sensing, and quantum communication. And there's also another really trending concept lately, which is the so-called quantum internet. And I think it's kind of interesting because it makes a sort of bridge between all those areas. So why can we say that? It's because the idea of a quantum internet would be a network of quantum computers that are interconnected by quantum links. And we could use this network to run some protocols such as blind computing and distributed sensing that we've been hearing about in the last talk, but also secure communication that I'm going to talk about in this presentation. So in all those applications, a crucial resource is quantum entanglement. And this is really going to be also very important in the work that I'm going to present. Oh, sorry. Okay. So what do I mean by quantum entanglement? So we all have different backgrounds, and I want just to clarify what I mean by entanglement as an experimental physicist. So in my world, as I would say, I'm going to deal with polarization entangled photon pairs. Okay. So the idea is that I consider a source that can emit a state of the electromagnetic field that I can write in this way. So we call this a Bell state. And the two photons generated by my source have a crossed polarization. Okay. So here HV and VH. So I can send those photon pairs to different parties. Okay, so here Alice and Bob. And so what it means to have entanglement is that this state cannot be factored between the two Alice and Bob subsystems. And for more practically, what it means is that I have a kind of spooky action at distance, to quote Einstein, between Alice and Bob, which means that if one party measures his qubits, it will project the state of the other qubits at the other station. So those non-local correlations are typical of entanglements, and you can check that you have this kind of correlation by some tests, such as the violation of Bell's inequality. So in this talk, I will use a specific measure for entanglement, which is the fidelity, which is a quantity that tells you how close the state of your source is to an ideal Bell state, such as the one written above. So entanglement is nice, it's beautiful, and it's really useful for quantum information. And that's why people have been really striving to build a network that can distribute entanglement over very long distances. So how it works is, in this kind of networks, we want to have three building blocks. So first, a source of entanglement. So in my case, it will be entangled photons. So for this, you have several platforms, such as nonlinear crystals and also photonic chips, which are kind of the miniaturized version of the latter. And so I'm going to focus more on these. Then when you generate your entanglement, you want to be able to distribute it to long distances. So again, you have several strategies and several very, very interesting results that have come up lately. So first, you can use free space links. So here in this experiment by the group of Janwei Pan, people have been sending a source of entangled photons in space on a satellite, and they've been distributing the entangled photons to locations on the Earth. And they've checked that they still have entanglements, and they did some quantum key distribution protocols, so over very, very large distances. Another approach would be fiber links, because photons are light, so they can travel through optical fibers, such as our classical internet. And people have also been doing, so here in Vienna and Bristol, a kind of a network where they send photons to different locations on a city-wide scale. And again, they check that entanglement is preserved and that they can do some QKD protocols with it. And last but not least, I just want to mention, it's not going to be the scope of this talk, but what you want to be able to do afterwards is also to store entanglements. And again, for this, you have several platforms for quantum memories with also a lot of works and very impressive results lately. So in my work, I want to focus really on the entanglement generation and distribution parts. And what I'm going to show is how we managed to build a resource-efficient architecture that features a compact, very small and efficient source of entanglement and a flexible distribution scheme that is kind of the scheme that you have in the classical internet. So what we do in our team is we have an expertise on miniature chips to generate entanglement on chip. So you have here on the right an example of the chips that we make in our lab. So you see that it's quite small compared to this coin. And the basic idea is to miniaturize some optical components down on a micro scale. So a prototypical photonic chip would look like that. So you have a source of entangled photons, and then you can do some gates optically, okay? So it's kind of the equivalent of some optical setup. So this approach is very interesting, also very active field of research, because you can generate and manipulate single photons and entanglements on a microchip, which is scalable and compact. And so you can make those chips out of many different materials, and in our case, we use a semiconductor, which is called aluminum gallium arsenide, or AlGaAs. And I'm going to motivate why we choose this platform. So it's very nice for the application that we want for quantum network for several reasons. So it ticks all the requirements, it ticks all the box for the requirement for a good source. So first, it has polarization entanglement, which is really kind of the basic property that we want. So this has been checked several years ago by our group, and we see that we can really generate high-quality entanglement in polarization. Then we want our source to be bright, so to emit many, many photon pairs per unit time, and to emit those on a broad spectral range. So we're going to see why it's important later. And so this, again, has been demonstrated in our team and some others. And lastly, we want this source to be compatible with electrical injection, which means that we want to be able to plug our source to a battery, electrical battery, to generate our photons, which is kind of more integrated and also cost efficient. So again, this has been demonstrated in our team several years ago. So this is for the source part. So we have a good source, but also we want to integrate it in a flexible network management technique. So for this, we borrow some techniques from the classical telecommunication field. So much like internet at home. So the idea is that here you have a prototypical classical network where you have a central router which sends information in different fiber links, so here. And it sends the messages to the different end users. But also you see those kind of like color boxes here. And this is really a crucial point. It means that the links are so-called wavelength multiplexed, which means that you can send information encoded into different wavelength channels. And so the different wavelength channel will be routed to the different users in the network. And so it serves as a way to direct information and to manage information in the network. So wavelength is really the key. And lastly, what is also nice with the classical networks is that they are reconfigurable, which means that thanks to some specific device and the fact that you can use the wavelength to select and route the links, you can manage the network and change the configuration of the network dynamically, okay? And so we want to use this kind of architecture, but with our source at its heart. And so yeah, so the bottom line of this talk is this. So we want to use our on-chip source, embed it into a flexible, reconfigurable network, and obtain a flexible entanglement distribution scheme. So this is kind of the main idea, and here's the outline of the talk. So first I'm going to explain how our source of polarization entangled photon works physically. Then I'm going to show some results about long-distance entanglement distribution and quantum key distribution. And lastly, I'm going to show how we can build a reconfigurable multi-user network. So first, the source. So you've seen on the picture with the coin that on our chip we have several tiny lines, okay, so stripes. And so each line is what we call a waveguide, so that we've been hearing about also this afternoon. So it's a kind of a strip of material, so in our case, aluminum gallium arsenide. And it's kind of a tunnel for photons that can be confined and travel around along this waveguide. So it's a parametric source. We send a pump photon, and it generates two entangled photons in the telecom wavelength band. So it works like that. So it's a spontaneous parametric down conversion process, so pretty standard. Most sources work with this process. And one nice feature of our source is that we don't generate photon pairs at only one wavelength, but over a broad spectral range. And this is really important. And we've been, we can check that experimentally by measuring the number of pairs that we generate as a function of wavelength. And we see that they are distributed around a band of around 60 nanometers. So it's a lot of nanometers. And this state is centered in the telecom C-band, which is the band that you use for classical communication. So the wavelength, the region of the electromagnetic spectrum where telecommunication works. So our source is broadband, and it works at the right wavelength. So it's nice. So when I say broadband, what does it mean in terms of quantum states? Let's get more into the detail. So as I said, we have in our process, in the SPDC process, we have energy conservation, which means that the pump photon gives birth to two entangled photons with lower energy, okay? And the energy of the generated photon have to add up to the pump. It's energy conservation. And what I said is that you have several combinations of the energy of the generated photon that add up to the energy of the pump. So if I plot my spectrum, I can divide the spectrum of the two photons into many, many different frequency channels, okay? So it's as if I generate entangled photon states in the superposition of like the red channels, the yellow channels, the green channels, and so on. I have a pair that is distributed over many channels. And this is going to be a key point of our protocol. So the quantum states that we have, it's as if, it's really a crude approximation, but it's as if we had a collection of Bell states, but living in different frequency modes, okay? So it's as if I have, a Bell state in the mode, the red mode, in the yellow mode, in the blue mode, and so on and so forth. So what I want to do is quantify how much entanglement I have in all these modes. So to do that, I use a pretty simple experimental setup. So here on the left, I have the generation stage. So I generate my photons using a laser and our chip, okay? Then I collect my photons, which are here. And then I'm going to use a filter, so a wavelength selective filter, to select and route the different wavelengths in separate optical fibers, okay? So what I do is that, for instance, I select the red channel pair, and I send one photon in one arm and one photon in the other arm, and then at the end, I use some optics to project the states on a given basis. So what I do is that I do some measurements in 8 different basis configurations, and they can be used to estimate the entanglement. And so I do that for all the available channels in my state. I just chop up the spectrum in the different channel pairs. So I showed this for the red channel pair, but I can do it again for the yellow, for the blue, and so on and so forth. And I can analyze how much entanglement I have in each channel. So to do that, I compute the fidelity that I introduced at the beginning using those 8 measurements. I can do it experimentally. And if I check the value of the fidelity as a function of the frequency, I see that I have a region where it's close to 1 and then it decays, okay? But still, I have a very broad region of my spectrum where I have a good fidelity, so a good entanglement. So in terms of number, it's around 26 nanometers for fidelity greater than 90%, which kind of is as good as the state-of-the-art sources. Yep.
I know H&V is horizontal and vertical, but what is A and D?
Okay, so here horizontal and vertical are, okay, H&V are horizontal and vertical, and D and A, they are diagonal and anti-diagonal, okay? So maybe I should have written down. Thanks for the question. Yeah, so we have entanglement over a very broad band, very broad frequency band. So now we want to check that entanglements can be distributed at long distances, and we show what we can do with this entanglement in terms of protocol, quantum information protocols. So what we did is that we slightly modified the experiment, and we just added 2 spools of optical fibers here to add some fiber distance, and we check the entanglement after the photons have traveled through the fiber using the same kind of protocol. Yeah, so that's a picture of the fibers. It's simply bare fiber in a kind of a roll. And so the result that we obtain is this one. So we did this into 2 configurations. So with a symmetric link where each user are at the same distance from the source, and one asymmetric link where there's one distant user and one local user. Okay. So we did this because in real-life networks, you can have different links with different length, and it's important to check that entanglement is robust against this kind of asymmetries. And when you look at the fidelity as a function of distance, you see that it stays around 1 for almost 100 kilometers, and you can even extrapolate to higher distances. So we see that we have a fidelity that's greater than 90% over like more than 100 kilometers, which is kind of the scale that you want for a city-wide network. But then I just showed that I have entanglement. But as we said, entanglement is a resource with which you want to do some protocols. So what we chose is quantum key distribution, which is kind of the paradigmatic protocol that you can do with entanglement. And we decided to run the BBM 92 protocol, which really relies on entanglement. So if you don't know what this is, I'm going to just tell a few words about this protocol and how it works. So basically the idea is that we start with our state, so the psi plus Bell state. And here it's written in the Z basis, and I can also rewrite it in the rotated X basis. So with here D and A being the diagonal and anti-diagonal polarization. And what happens is that the source distributes the photons to the 2 users, and they can choose whether they want to measure the qubits in the X or in the Z basis. Okay. And what happens is that they see which of their detector click, and they accumulate a series of bit strings that constitute the secret key. So that's the output that they have, and because the photons are correlated, so they're entangled, the keys themselves are going to be correlated. So what happens is that if a malicious party tries to spy on their communication and intercept the qubits and measure them, it will destroy the correlations induced by entanglement. And so Alice and Bob can check, using some checks in their key, that entanglement is still there, and whether or not they have to abort the protocol. And so here we see that entanglement is really a key. It guarantees the security of the key. It's really at the heart of the security of this protocol. And also, a nice feature is that you don't need to trust the source, because they can check independently of the source that there is entanglement. Okay, so this is really important for network, the fact that you don't have to have a trusted node for the source. So what we did is that we decided to apply this protocol with our system. And yeah, we measured the 2 figures of merit of this protocol. So here the key rate, so the number of key bits that you can generate securely per second. and the error rate in the key, okay? And so we did that for all the frequency channels of our source. We see that we have quite a high key rate, okay? So around 40 bits per second, which for this kind of protocol is, again, close to the state of the art, and very low errors. So we see that we have high-quality entanglements propagating at long distances, and we can even do some QKD with it. So it's quite nice. So again, you want to do QKD not at 0 kilometer like here, because there is no distance here between the source and the parties, and you want to go long distance. So again, we repeated the experiment by adding some fiber distance between the two parties. So again, with a symmetric and asymmetric configuration. And so again, what we see is that here in red we have the key rate, in blue we have the error rate. And we see that in both configurations, the key rate, so it decays as a function of distance, as expected. And when you add all the effects arising from the finite size of your key, okay, which is really what matters in the real life, because keys are exchanged in finite blocks. So when you add the correction for the finite size sample, we see that in both cases, we have a positive key rate up to 75 kilometers. And again, this is nice because it's kind of the length scale for a metropolitan city network. Okay, so this is nice, but so far I've only shown results involving two parties, okay? So the source sending photons to only two recipients. But I have said that I want to do a network, so I want to go from 2 users to many users. And there's a trick to do that using only one source that is broadband. And it's been developed in the two following papers that are quite new as well. Well, still a few years ago. But the idea is to use the fact that we have many channels, as I've said, and we want to distribute those channel pairs in a smart way, such that every member of the network shares entanglement with the rest of the users. So here, for instance, I send the red channels to Alice and Bob so they can share entanglement through the red link. I send the yellow one to Chloe and Alice so that, again, Chloe and Alice share entanglement, and so on and so forth. And if I look at the topology of my network, it's really a complete graph where each user share an entangled state here represented by a line, okay? But this entangled state lives on a different frequency mode. So I can manage my frequency mode such that each user share entanglement with all the rest of the users in the network. So we've been doing this again in the lab. And what we've been using is, so experimentally, it's again the same device. So it's called a wavelength selective switch that allows us to route the different frequency channels to different optical paths. So this is what enables us to do this operation where we distribute the channels to the different parties. And again, this device is quite nice because we can also change the size of the channels, and we can just, again, like the classical internet, we can use broad channel with a broad bandwidth or very narrow channel with a small bandwidth. And if we use very broad channel, we can fit 4 users in our network, but each user will receive a lot of photons. But if we lift the restriction on bandwidth, we can go down to, for instance, very tiny channels of 50 gigahertz, but this time we can fit 8 users in the network. So by changing the channel size, we can go from 4 to 8 users. And this without changing any hardware, because this can be done dynamically with this device. So this is kind of nice because we can distribute entanglement to many users at a time without changing anything in our setup. And so in terms of measurement here, those graphs are simply the time correlation between the photons arriving at each user. So for instance, here in the 4-user case, you have 6 links, sorry. So you have 6 peaks corresponding to the arrival time of the photon pairs for each pair of users. So here you have 5, here you have more because you have 5 users, and etc. So here each peak represents one link in my network. So I check that the signal is the same for all the links, and so I have a kind of a balanced network. But in real life, things don't work this way. You can have some physical constraints coming into your network. And we've been also finding a trick to solve that. So imagine a very simple network with 5 users, and you have one user that is very far away from the source. So this can happen physically, in real life. So we used a 25-kilometer fiber to model kind of this distance. And what happens is that the link between Bob and the rest of the 4 users will be smaller because of the losses. And what we want to do is to change the bandwidth of the channels such that to give Bob more bandwidth such that it counteracts the effect of the losses, okay? So we go from wavelength configuration where all the channels are even to one that you have broader channels for Bob and Chloe, Bob and Alice, Bob and Etienne, Bob and Diane, such that it counteracts the fact that Bob is located more at a greater distance. And so you see that in real life it works. If you measure the signal across all the links in your channel, you see that you go from an initial configuration where you have the 4 links that have more losses, which have less signal, and then when you balance your network using this kind of technique, you can have an even level of signal for all links. So it's kind of a sort of prototypical smart quantum network where the network can adapt to an external constraint. So again, this is kind of nice in the prospect of future quantum internet. Yeah, so we're coming to the end of my presentation. So to summarize, I've been showing you how our entangled photon pair source works. So it's compact on-chip source. Then I've shown some results on long-distance entanglement distribution and QKD. And then we've seen how we can build a network that is flexible and that can adapt to some constraints dynamically. And what we want to do in the near future would be to try to deploy this protocol on a real metropolitan link between our 2 labs, so Lipsis and Jussieu, and maybe try also new network topologies where the network is not necessarily a complete graph, but maybe other richer class of networks. So yeah, if you want more information, please check out my archive paper if you're interested. And I want to thank all the people who worked on this project. So Sarah Ducci, my PhD advisor at MPQ, Florent Babou, Maria Amanti, and also Eleni Diamanti at Ellipsis, and Fabien Boitier at Nokia Bell Labs. So I hope it was interesting, and I'd be welcome to answer any question.